afternoon. So before we dive into the presentation, let me give some Classiq updates. So Classiq is a leader in quantum software. We are a team of 70 quantum software engineers, quantum algorithm developers, based in Israel and also in New York, Amsterdam, and very soon in Tokyo as well. Our platform is being widely used in industry and also for research and education. And this is also a great opportunity to thank our partners who really make our work much more meaningful and user-oriented. So thank you so much. When it comes to quantum readiness, we want many things, right? We want applications. We want them to be NISQ, but also large scale. It should be hardware agnostic and production ready and abstract, but not too abstract because it should be also optimized and scalable. And we want to create assets. And it is not possible, right? We are very, very far from anything that is production ready, anything that is scalable, definitely not abstract or optimized. And that's a problem. But we shouldn't feel too miserable or too spatial because similar design challenges were already solved in other industries. So let us have a look. 60 years ago, when engineers wanted to design buildings, they needed to take care of literally every building block, right? Every tiny detail, and it could take months, even years, super unoptimized. Today, it's not the case, right? With Autodesk, you can create a model of the building, and automation does the hard work of implementation. Chip design, which is closer to our field, was the same story, right? Back then, at the late 60s, as the number of transistors on a chip raised to a few hundreds, with few hundred gates applied on them. Sounds familiar? So it became impractical to design at the gate level. And therefore, electronic design automation methods were developed. And today, you can relatively easily design chips with billions of transistors because you build the model and automation does the rest. This is Classiq. This is what we bring to quantum software. Classiq automates the design of quantum circuits, allowing abstraction, scalability to any number of qubits, usability, optimization, and production-ready quantum software. But before we dive into what we do, let's take a look at what is being done today without Classiq. So today, when you develop quantum software, most of the process is manual, right? You need to define the desired functionality, to use some building block or algorithmic scheme to adapt it to your use case, to optimize it, to adapt it for a specific hardware. And the last mile is automated, right? Compilation, transpilation, which are both super important, but also very limited because the design space is huge. The flexibility at the functional level is huge. There are so many different implementations for the same functionality. But eventually, you develop a quantum circuit and you send it to the compiler, and the compiler is very limited, right? What it can do. You design the shitty circuit, so okay, it will do what it can, but it's not much. Let's take a look. Let's take a look at multi-control X, which is a very common building blocks in many quantum algorithms. And let's take a look at its design space, right? Let's take 6 points on its design space, 6 different implementations of the very same functionality, and you see very different circuits. Some are deep, some are shallow, some use more qubits, some less, but all with the same functionality. So how should the developer know how to design these circuits? And again, this is a very tiny part of a very large algorithm, so obviously it's impractical. But you shouldn't do that, right? Because what we do is automating this process. What you need to do with Classiq is defining the functionality. There is a full separation between the functional model and the hardware constraints, right? Because the functional model remains the same. You can adapt it, you can change it, but on a basic level, it remains constant. The hardware constraints change every day. So when you let automation choose the optimal implementation for your specific functionality, taking the constraints into consideration, so on the one hand, obviously, it's much easier, it's more abstract because you focus on what you want to do, but also you can get much, much, much better results. And let's come back to our MCX friend. So you see here some comparison between Classiq with this design flexibility and Qiskit, which is fantastic, but there it's a building block with no design flexibility. So when you give the synthesis engine this flexibility to use some more qubits or different implementation, you can save up to 97% in circuit depth, which is obviously dramatic. The Classiq platform, eventually, it's a one-stop quantum shop from high-level modeling of the circuit synthesis, analysis, debug, and execution. It's integrated on top of all available quantum clouds, simulators, also directly with some of the with some of the hardware providers. And let's have a look at how it looks like, right? So this is the Classiq IDE. On the left, you see the functional model that could be created in Python or in a graphical interface. And again, there is a full separation between the model and the constraints. Now, let's add the constraints. We want this to work on maximum of 11 qubit, circuit depth up to 250. We could also load a preferred gate set and noise model and so on and so on. But now we'll just synthesize the circuit. It will take probably 2-3 seconds, and the circuit is being created. Now you are moved to the circuit analyzer, which allows you to debug the circuit, to analyze it. You see that the circuit depth is 90, which meets the constraints. You open it, you see it's not super complex, but it would be challenging to design it manually. And you can also get many insights on each of the functions. And of course, this is very important for explainability of quantum circuits. Now you want to execute. So you can choose Bracket, Azure Quantum, other backends. Let's run it on the IBM simulator just for the sake of time, and you get the results in another second. So really end-to-end production-ready software platform. This is an important takeaway. A quantum model is built to last, right? And this is unlike a quantum circuit that may be good for today, but tomorrow the hardware was changed and it's pretty much irrelevant. And why is that? Because again, you have full separation between functionality, which could remain stable over time or adapted or grow with the company knowledge, and the constraints which are constantly changing. It means, for example, that if you build a sophisticated model today, maybe the constraints are unsatisfiable. You just can't run it on today's machine. But in 2 years from now, the very same model, the very same asset will be useful. All of a sudden, the hardware is there, and you can really take advantage of what you created now. So the main takeaway is if you really want to build something that is future-proof, you should build models and not a quantum circuit which really lasts one day, even if it took months to create it. And now let's talk applications, right? We are here for applications. So obviously, it's very easy to define more and more applications on top of the platform. But you will also find there vertical-specific application suites in many industries, aerospace, automotive. Let's, for now, take a look at the finance application suite. So you'll find there all available, implementations, model of portfolio optimization and option pricing, and all sorts of exotic option, Bermudian options, HHL-based, and so on, fraud detection. And again, it's really easy to take a basic model and to adapt it to your needs and to different hardware backends. Before we finish, let's take a look at some recent highlights and recent work. As I said, the platform is really used for in industrial use cases, for research, education, for NIST implementations, for fault-tolerant via the cloud in HPC, and I do want to give some examples. So the first one is a really beautiful work done by the Rolls-Royce team who modeled the HHL algorithm for computational fluid dynamics. This is super complex algorithm with many non-trivial functions within it. So this is really impressive work by the Rolls-Royce team. This is another example for education. The platform is used for quantum computing research and education in many universities. This example is for Carnegie Mellon, where the Classiq platform is used to teaching quantum computing software for the next generation of quantum software engineers, which is very, very important for us in order to build this community. We said that we are very focused on all of the spectrum. And in order to take the full optimized path from circuit design, circuit synthesis, and optimal execution, we partnered with Q-Control, and we integrated on top of FireOpal. And this is really by far the best way to squeeze as much signal out of today noisy machines. And on the other hand, we also look at the algorithms of tomorrow at quantum at scale, right? This is really beautiful work done with Microsoft Resource Estimation Platform, which really closes the gap between quantum algorithm on academic paper to executable code. This is a huge gap, and let me take a bet. You have ever built a Shor's algorithm, which on paper looks very smart but very simple, but when you try to implement it, that's a tough one. But when you automate the process and all of the difficult functionalities are being automatically designed, this is much easier. And of course, when you use the Azure Quantum fantastic resource estimation platform, you can also analyze the results and understand when it will be really executable. Last but not least is a teaser for tomorrow's talk with HPE and Classiq about how we build together the quantum stack for HPC on top of the Cray stack. This is very important because obviously quantum and HPC are going to be tight in the coming years. Everything is going to be hybrid, and building a quantum stack dedicated to HPC users is of high priority for us.